Welcome to Study Loop.
Okay, so today we will be doing problem 71 from chapter 17. So as you can see, it's a titration problem. So from the get-go, I always tell my students to be very sure about what they are trying to accomplish in each problem. So a titration is pretty straightforward. It's an acid plus a base that gives you a salt and water. Now, something I always tell my students is that you should never forget that there is water in this half too. Every time we use acid or base solutions in a lab environment, we dilute it down. There is always no situation where you're using pure acid or pure base. So while acid and base together might react to give you water, there's already water in this solution here. And this is very important to remember while solving problems. Some people forget it and they run into issues. So from the get-go, I want everyone to know that there's water already in the mixture. Okay. Now the second problem that people face is which one's the acid and which one's the base. If you look at our problem here, you have methylamine and HBr. Now it's very easy to say HBr is the acid, but in some other cases, it might not be that simple. So as a rule of thumb, I always react my reactants with water first to check which one's the acid and which one's the base. So in this case, you're gonna get CH3NH2 plus and OH minus. Since you get OH minus here, you know that this reactant right here has to be a base. The second thing is reacting HBr with water. You already know this is an acid, but I'm still going to go ahead and do this just for consistency's sake. So you get Br minus here, and then you get hydronium ions. So since you get hydronium ions, you know that this is an acid. Okay, moving on. These two here will give you your salt, and these two here will give you water. The salt here is CH3NH2 plus Br minus. Some people don't like to use these signs, but if you want to, you can always do that just to keep track of what your anions and cations are. Okay, so this is the basic idea. Once you have this down, you can tackle almost every other problem. New page. The first thing is they want us to calculate is the initial pH. To know the initial pH, you have to know the initial state of the system. And in the initial state of the system, before you add the acid, you have a beaker that has 25 milliliters of 0.175 molar CH3NH2, which I hope you guys remember is the base. pH is a straightforward equation. It's minus log of H plus ions But the first mistake that people make is they try to plug this value directly into this, which is wrong. Why is it wrong? Because a base will always furnish OH minus ions, not H plus ions. So if you put this molarity here, you're getting the wrong answer. How do we calculate the H plus ion concentrations? You use the ionic product of water. So the ionic product of water, or the product of H plus ions and OH minus ions, is always 10 to the power minus 14. So simple math. I apologize for my clock. We're just gonna let that run while okay. So you have to find the concentration of the OH minus ions, which is pretty simple because you have over here 0.175. Divide this and your concentration of H plus ions is 5.714 into 10 to the power minus 14. So go ahead and take this value and plug it in here, and you'll get a pH of 13.24. Now don't blindly accept any result you get. Ask yourself, is this reasonable? So since we started off with a beaker of primarily base, of course there's water added in, but it's primarily base, having a pH of greater than 7 seems reasonable. So we can assume that our answer is correct. Now the second part asks us to calculate the volume of added acid required to reach the equivalence point. Now for this, you have to understand the concept that at equivalence point, the number of moles of acid have to be equal to the number of moles of base. How do you calculate the number of moles of acid? You multiply the molarity of the acid by the volume of the acid. And for the moles of base, you multiply the molarity of the base with the volume of the base. So the molarity of the acid as given in our question is 0.150. So molarity of acid 0.150. Remember that the volume of the acid is what we need to find, so it's the unknown quantity over here. The molarity of the base 0.175. And the volume of the base is 25 milliliters. Now, as a rule of thumb, I always convert all my units to liters. So if I have milliliters, I'll convert it to liters. In this case, since the other value you're trying to find is also a volume, it won't matter if you have milliliters here or if you have liters. But just so that you don't get your units mixed up, always convert your volumes into liters. So the volume of added acid is 29.16 milliliters. And this is how much you need to neutralize your solution. The third question is, what is the pH at 5 milliliter of added acid? So first, let's look at what's happening when you add 5 milliliters of acid. Remember, our acid here is HBr, so you're technically reacting CH3NH2 with HBr, and you get the salt that we discussed in the first window. I'm going to quickly show you the first window again, just to refresh things. So this is the salt we got, right? So it's the same salt here. And we're trying to figure out how much of this salt was produced. So we need to start with the number of moles of methylamine, which will be the molarity multiplied by the volume. The number of moles of HBr added, which will be molarity into volume again. And then initially this is 0. These values, I've calculated them. You can calculate it again just to check. Is 375, and here it's 0.00075 and 0. So when a reaction happens, some of your reactants get used up. In this case, 0.00075 moles of acid react with 0.004375 moles of base, and the acid, since it's the smaller amount, or it's not in excess, is completely used up. So here we have 0, no acid is left. The amount of base that's left behind, because remember it was in excess, so some of it is still in your solution, and the amount of salt formed will be 0.00075, right? Now you have the task of finding the pH. pH again, really simple, minus log H plus. Be careful, because again, the first mistake people make is they try to plug this in here, which is wrong for 2 reasons. Firstly, it's not the molarity, it's the moles, right? Because you calculated moles here, so you can't plug it in directly. And secondly, it's, even if you did find the molarity, it would be the molarity of the base, not the acid, which is what you need. So here we quickly use our ionic product. Put this one here. Okay, now comes an important step. You have to find what OH minus is in this case. So OH minus obviously will be the moles of base that's left divided by the volume of the solution. Now remember, it's a volume of the solution, not just the volume of the base. So you have to add this and this quantity together, because that's how much solution is in there. Add it up, divide by 1000, because remember we convert everything into liters, and this is your OH minus. So now you can go ahead and plug this here, and you'll get a pH of 13.08. So again, you ask yourself the question, is this reasonable? Since you still have excess of base and all your acid got used up, so having a pH of greater than 7 makes sense. However, if you compare it to our previous pH, you see that it's slightly lower, it's slightly more acidic, which makes sense because now you have added a certain amount of acidity to the solution by adding HBr. So it will be lower than our initial pH of 13.24. Okay. Next question. The pH at 1/2 of the equivalence point. Now, whenever I see questions like this, I always try to figure out what the question is actually asking me. So I know I have to find the pH, but what is 1/2 of the equivalence point? So I go back to what my equivalence point was, which was 29.16. So half my equivalence point, which is divided by 2, will be 14.58 milliliters. So essentially what they're asking me is what is the pH when 14.58 milliliters of acid has been added. So I can do that because it's pretty similar to what we did in the part before. I write down my reaction. I write down my product. Okay, now since we've already done this calculation before, I will just copy it from the previous work we did. HBr we need to calculate separately because in the previous case you added 5 milliliter, but in this case you added 14.58. So on the side, so remember what I'm doing here is 0.15 into 14.58 divided by 1,000. That value comes out to be 0.002188 and it starts with 0. So again, this is greater than this, so this is in excess. Base is in excess. Acid is in a smaller quantity, so when you subtract this amount from this, you are left with 0.002187. This is 0, and the amount of salt you formed is 0.002188. Again, you're tasked with finding the pH. It's minus log H plus. Caution, do not put this here. This is moles, and also if you convert this into molarity, it'll still be the molarity of the base, not the acid. So we have to use the ionic product, 10 to the minus 14 OH minus. How do we calculate OH minus here? We take our amount of salt formed divided by the volume added, and in this case we added 14.58 milliliters of acid to 25 milliliters of base. So our volume here will be 25 plus 14.58 divided by 1,000. There you go. You can happily plug this in here, and your pH will be 12.74. Is this reasonable? It's still pretty basic because your acid was not in excess. Your acid got used up and you still have base left. So yes, the pH being greater than 7 makes sense, but it's more acidic than our part C because in part C you only added 5 milliliters of acid, and it's also more acidic than part A because in that case no acid was added. So logically all of this makes sense up until now. Okay, so this is going to be a tricky one. Our next question is pH at equivalence point. pH at equivalence point. What is equivalence point? Let me go back. 29.16 milliliters of acid. Now immediately we are running into a problem here. And the problem is at the equivalence point, the acid has been completely neutralized by the base. So you don't have any acid or base left to do your pH calculations, because the H plus or the OH minus ions are now no longer coming from the acid or the base. Let me show you why the technique that we've been using so far will no longer work here. So this is my reaction. I could choose to start off with 0.004375 like we've always done, calculate HBr, which will then be 0.15 multiplied by 29.16 divided by 1,000. You plug this in here, which is 0.004374. This is 0. And what happens? So this and this value is very close together, right? So the amount of base left over will be close to 0, and the amount of acid left over will be 0. And then here the amount of salt formed will be 0.004374. If I were to use my pH trick and I wanted to enter the molarity of OH minus ions here, this would absolutely not make any sense anymore. So we're gonna use a different method, and that method requires an understanding of the hydrolysis. CH3NH2 in water solution will give you CH3NH3 plus OH minus plus HBr. You start with the concentration of C, nothing here, nothing here. Some amount of it gets hydrolyzed and you end up with X moles of this and X moles of that. Now the Ka of this reaction will be 10 to the power minus 14. The Kb of this reaction, we can go into the concept of this some other time, but right now I'm just focusing on how to solve this problem. So in another segment, I will go through why we're using this formula over here. In most cases, X is so much smaller than C that we can ignore it. So X squared divided by C. This is a value that you have to know. It'll probably be provided to you. And Kb is 4.4 into 10 to the power minus 4, right? So your reaction over here will be equal to 10 to the power minus 14 divided by 4.4 into 10 to the power minus 4. C is something you can easily calculate. You remember we started with 0.004375. You added 29.16 milliliters of acid to completely neutralize it and divided by 1,000. And the C, once you plug it into here, gives you the value of X. And you can do this yourself. I'll give you the answer. It's 1.35 into 10 to the power minus 6. Now, a couple things before we go on to the next page, because it's going to be a continuation of this part, is that the amount of HBr produced is X. The value of X is 1.35 into 10 to the power minus 6. HBr is a strong acid, so the tendency is that HBr will not stay as HBr but break up into H plus and Br minus ions, right? So if I had 1.35 into 10 to the power minus 6 in HBr concentration, that will be broken down into 1.35 into 10 to the power minus 6 H plus ions concentration and 1.35 into 10 to the power minus 6 Br minus ion concentration. If I want to do pH here, pretty straightforward because it's already an acid and this is already a concentration. Remember, we used concentration values here. We did not use moles. So this value you see here is in molar. So you plug this in here and you get a pH of 5.8. Now stop and ask yourself if that's reasonable. So you started with base, you completely neutralized it with acid, but the salt you formed, which is this, hydrolyzes to give a weak base and a strong acid. A weak base and a strong acid. This will not ionize. This will ionize. And when it ionizes, it will give off H plus ions, which will make the solution acidic. So at your neutralization point, you will have an acidic solution. So having a pH of less than 7 makes sense. Okay, almost done. Now the last question is pH after adding 5 milliliter of acid beyond the equivalence point. This should not be difficult at all because here we already have the concentration of H plus ions, right? H plus ions will be 0.15 into 5 milliliters. I'm going to divide that by 1,000, thumb rule. The amount of solution is 25 from the original base, 29.16 from the acid that you added, and then 5 from the additional amount of acid that you added beyond the equivalence point. So all of this is gonna be plugged in right here. And again, this is molarity, so you can put that in directly, no worries. And you get 1.896. So does this make sense? It's less than 7. You have a solution that was already kind of acidic, and then you added more acid. So yeah, this makes complete sense. And so we have solved all the parts of the problem. Okay.